Hi there, I'm Scott Lowe with ActualTech Media. I'm here today at WekaIO, where I'm joined by Andy Watson, who is the Chief Technology Officer. Andy, thank you for having us in your offices today.
My pleasure. Thanks for coming.
So one of the things people like to understand is how things work. Can you tell us basically what the innards of WekaIO look like so that people can understand how it works its magic?
Well, I would enjoy the opportunity, and please ask questions as we go along.
Absolutely.
We have set up a whiteboard for this purpose. So I think it's really important all the time to focus on what the application is trying to do. And I think if you start out with that orientation, and we'll start out that way in our diagram, you have an application server, and the server is generating I/O, right? It could be a GPU accelerated server perhaps, which even makes it more intense, right? The amount of I/O it can generate. Traditionally, it might have been doing its I/O with, let's say, NFS, right? Especially if there was a huge amount of data in the data lake that was being shared, it would naturally go toward a kind of an NFS style solution. And that would be fine up until the recent era when GPUs demanded more I/O than NFS could deliver to a single mount point.
Right.
And that's a whole topic in itself. Maybe we'll do another talk about that, but let's leave it there for now. What we also offer, although we do support NFS, is we also offer a mechanism whereby you can use a POSIX compliant local file system representation, which is delivered by our WekaIO client. All right, so we install that. It runs in user space, and it is very lightweight, very small memory footprint. And the idea is that by having this available to the application, you don't have to rewrite your application. All of the system calls that the application makes to access its files, its data, and so forth are fully supported. And by being POSIX compliant, it means that none of the semantics change in any way. It looks like it's accessing local storage, but in fact, as you can see here, it's going out over, let's say there's an Ethernet or InfiniBand. Now, having gone out over this network, and let's hope it's a high-performance network, this is not the dark ages of networking anymore. It could easily be 100 gigabit networking, because that's roughly the same cost as it would have been, say, 10 years ago to go with 10 gigabit. So I encourage any of our customers to at least consider making that investment today, because there's really no reason not to use 100 gigabit. If you're using 100 gigabit, the latency is so low. And actually, even if you're using 10 gig, if that's what you already have as your committed investment, the latency is still very, very, very low compared to the overall latency of a read or a write. There's no reason not to go over the network to access your data. Once you're going over the network, you can reach our systems. And our systems would be a minimum of 6 or more nodes that are storage nodes in a cluster.
How far away can these storage nodes be? Because obviously the longer the distance, the more the latency. So are these local? Are these stretched? Where are they located?
This is a local area network solution.
Okay.
All right. And indeed, for 100 gigabit, it would be difficult to do it over a great distance.
It would.
Yeah. So now, we're on this network, in this storage node cluster, right, we're running what we call our back end. And the back end allows this cluster of WekaIO nodes to communicate and to deliver a distributed, fully parallel file system. And one of the things that's very different about our implementation from anything else the world has ever seen, and I mean that very specifically, is that the metadata associated with the file system. Metadata is the data about the data. It means tells you where the data is, what the permissions are, and so forth. That's ordinarily the bottleneck. It's the limiting factor for how much I/O you can accomplish when the application is trying to access the data. Our metadata is fully distributed. It uses all the resources. Now, I said the minimum is 6, but it could go up to, we've tested to 4,096, and it could go as high as over 64,000. This is an incredibly scalable solution. And when you scale, unlike, again, other solutions that people may have had some experience with, what you're getting is more resources available for more capacity, more devices, because every one of these systems has SSDs on it, preferably NVMe devices for the best possible lowest latency storage. And more devices means more parallel access to more storage media. And the metadata that I was just
Scales along with it.
Scales with it. Other solutions will do something like segregate the metadata and say, oh, metadata is very important. I'm going to park it over here. I may apply a special database to it. Whatever they do, again, because it's segregated, it's limited in its available resources. Inevitably, it becomes the bottleneck. And here's how it manifests, right? They'll say, be careful, don't put too many files in a directory.
Yeah, and we've heard that. I mean, looking at other solutions, we've always seen these limited metadata pools, basically, and it would be a limiting factor because we've seen the don't put too many files in because they know their metadata can't grow to support that many files, and they're going to end up with performance issues as a result.
And they'll say, oh, well, don't worry about it, just start another directory, right? Just split it up. Well, splitting it up may not have been that big a deal 20 years ago when these other file systems were originally designed. But nowadays you have IoT and autonomous vehicles and automated manufacturing processes and so many sources of data pouring into these data lakes where nobody has the time to be doing this house cleaning, or if they do find the time, it's time that's stolen away from their real work, from their research, in order to do what? To segregate their data according to some arbitrary schema so that they don't overload directories in the file system. We can literally, I mean this with no exaggeration, it's not a hand wave, we can put trillions of files in the same directory, and it makes no difference to our performance or stability because of the design. How can that even be possible? Well, when our founders were designing this in the first place, starting in 2013, and they worked for several years before it ever saw the light of day, they were only writing it for flash. They were not writing it for hard disk. In fact, our flash file system doesn't work with hard disks. For hard disks, we tier out to S3 storage to allow you to put petabytes upon petabytes, exabytes, wekabytes of data out into hard disk. But our file system with its metadata only runs on flash, and as soon as you're only running on flash, you realize that every cell, every block of data can be accessed directly, direct access, so you no longer have to worry about cylinder groups.
Parallelism and things like that you can't get with hard drives either.
Right, parallelism, direct access, and you no longer have physical geometries to accommodate.
So question, if you have to put something on an S3 on hard drives, you're still storing the metadata here, so you're getting the benefit of the acceleration from the metadata up here?
That's very perceptive. The metadata is here. We can put the data out into the S3 layer. The S3 layer can scale, and we scale the metadata however it needs to be scaled with amazing performance. Now, when the application needs its data, even if the data has been tiered out to this layer, the first thing you do is find it. The first thing you do is determine that you have permission to access it and so forth. We're doing that right away, and we're going to go ahead and get the data that you're going to be asking for so that this is totally transparent to these applications. Whether you have a petabyte out here, 100 petabytes out here, an exabyte out here, it doesn't matter. So we scale this solution beautifully.
That's awesome. So out here, it may be a little slower, but the metadata piece isn't going to slow it down. It's going to basically be the physics-induced issues with hard drives that bring data back. But if it's all up here, it's going to be pretty instantaneous. Right,
and indeed, for the actual application throughput that our users report back to us, they're unaware of it being slower at all because the overall system performance smooths out the apparent or perceived experience that they're having at the application layer.
And is this tiering automatic, or is this something the user has to do?
So it's automatic, although the administrator gets to define some policies that would determine the priority for some files to be more likely to be tiered sooner than others. So you get to set policies, and then ultimately there are things like LRU, the least recently used data will be more likely to be tiered than the most recently used data.
Very good. Andy, this is a great overview of how WekaIO's architecture works. Thank you so much.
Oh, you bet. There's so much more I could tell you, and I've left out a couple of very important bits about how all of our software is written outside the kernel in user space, and we don't use any of the kernel's drivers to go to the SSDs or to go to the network interface cards. That's another way that we get very, very low latency. I mean, we could go on and on and on. I could spend an hour telling you about those details.
Are you actually rewriting firmware on the devices, or are you talking about something else?
We have our own, we don't change the firmware on the devices, but we have our own equivalent of drivers for talking to the firmware. And we bypass the kernel's drivers when we're talking to the SSDs and we're talking to the network interface cards. I did want to squeeze that in the last minute there because it is actually a very important part of the way we get our lowest latency. And because all of our software is running outside the kernel doesn't get to interrupt us. So we run the equivalent of a real-time operating system in that the I/O event runs to completion every time without being interrupted.
That's interesting. So you're bypassing all the scheduling mechanisms in the system and doing your own, basically.
Absolutely.
That's brilliant, actually.
Yeah.
Very cool. Thank you so much.
Well, thank you, Scott. Appreciate the time. Thanks for coming by.
And thank you to our audience for watching this video.